Alrighty, so we're moving on here to presenter number 5 is Anastasia, who is mentored by Nathan Roth. I think all of you are here. Nathan, would you like to introduce your intern?
Sure. Can you hear me?
You're a little light, but we can hear you.
Oh,
There you go.
I'll try and hold this a little closer. Anyways, Anastasia is a rising senior in high school, and this summer she worked on analyzing data taken with the ALMA radio telescope. This is a project that involves a technique in radio astronomy we call interferometry. And in my experience teaching this to people with, college degrees and PhDs, Anastasia did a fantastic job in tackling some concepts that can be daunting even to people with advanced degrees. So without anything further, I'll go ahead and I'll let her tell her all about the fantastic work that she's done.
Sorry, I'm trying to figure out how to share my presentation.
If you'd like me to share, just give me a holler and I can do that.
Yeah, that would be good.
Yep, I'm just opening it up.
All right.
Okay. Oh, it has me doing presenter mode, which I don't want to do. Hold on a second. Okay, here we go. And just let me know when you want me to advance.
All right. Hello, I'm Anastasia Markham, Nathan Roth's intern, and my project was on imaging and interpreting gas and dust emissions with ALMA for comet 2P Encke. Next slide. All right. Comets are celestial objects that orbit the sun along an elongated path. Comets are a comet that is not near the sun consists only of a nucleus, a solid core of frozen water, frozen gases, and dust. When a comet comes close to the sun, its nucleus heats up and releases a gaseous coma that surrounds the nucleus. The gaseous coma can be studied to determine the comet's characteristics, such as its chemical makeup and the kinematics movement of the emission in the coma. Comets are relevant to the study of the early solar system. When the area surrounding the young sun was a protoplanetary accretion disk, comets formed in the central cooler region of this disk and were then scattered to the outer reaches of the solar system, the Kuiper belt and the Oort cloud. After being preserved in a cryogenic deep freeze for about 4.5 billion years, the gases emitted by a comet and found in the coma can provide insight into the chemical composition and chemical interactions of the early solar system. So studying comets as they reach perihelion, which is their closest point to the sun, and peak in emission is very important. There are 3 groups of comets: Jupiter family comets with shorter orbital periods controlled primarily by Jupiter's gravity, Oort cloud comets with much longer orbital periods, and Encke-type comets, named after 2P Encke, which you may notice is the focus of this project. Encke-type comets are the least common kind of comets and are unique in their orbital characteristics. In the case of Encke, its short period orbit was controlled by Jupiter, but no longer is, making it not quite a JFC. Instead, its orbit is in a resonance, which causes its perihelion distance to gradually decrease, and in about 100,000 to 1 million years, it'll run into the sun. Next slide. All right, spectroscopy is a very common way to study space, and it was the foundation of the entirety of this project. Every molecule emits light at unique wavelengths along an electromagnetic spectrum. That's every kind of molecule, not every single molecule in existence, but yeah, like a spectral fingerprint. Knowing these wavelengths and being able to detect them and separate them from noise makes it possible to study the composition of an object based on the light that it emits. Yeah, next slide. Right. ALMA is, okay, the Atacama Large Millimeter Submillimeter Array is a multinational science project located on the Chanantor Plain of the Chilean Andes. ALMA uses interferometry. ALMA is made up of the 12-meter array containing 50 12-meter diameter antennas, and the Atacama Compact Array, made up of 12 7-meter antennas packed closely together and 4 12-meter antennas. This project used the 12-meter array to image Enki. All right, next slide. Interferometry, mentioned on the previous slide, is the method of synthesizing a much larger telescope by creating a network using multiple different smaller antennas. The distance between two antennae is called a baseline. Long baselines allow you to see fine details and fluctuations in brightness, but are blind to larger scale changes, and small baselines detect large scale changes, but cannot resolve variation on small and precise spatial scales. One example of an interferometer is the EHT, the Event Horizon Telescope. This array of telescopes is behind this famous image of a black hole in another galaxy. The EHT contains antenna telescopes across the entire world, as shown on the map, creating an Earth-sized telescope with incredibly long baselines needed to image the brightness fluctuations around a very distant object. Right, next slide. Enki is a point of interest in comet science. It made a very favorable apparition in 2017. That year, Enki was simultaneously very close to the sun and very close to the Earth, making it bright. Typically, comets so close to the sun that they are inside the orbit of Mercury are difficult to observe. In the few other comets that had been measured at such close distances to the sun, it is suspected that dust breaks down under the intense solar radiation, producing more product molecules detected in the coma. Observations made with ALMA can distinguish between dust and gas originating directly from the nucleus and originating from further in the coma, enabling us to test whether these behaviors are seen in Enki's coma. Enki had also been previously observed during a 2003 apparition, making it possible with the data collected in 2017 to test for changes in molecular abundances in the coma from one apparition to the next. This project focused on the molecules of hydrogen cyanide and carbon monosulfide. Hydrogen cyanide, or HCN, is typically a parent molecule in comet comas, subliming directly from the comet nucleus. It is an intrinsically strong transition and therefore typically easy to image. In other comets, HCN abundance in the coma dramatically increases when very close to the sun. It is not known if Enki follows this pattern, so HCN imaging is relevant in this case. CS is typically a product molecule or daughter molecule, on the other hand, being produced by chemistry in the coma when parent molecules break down, rather than at the comet nucleus. It's another strong transition. It is not very well understood what molecules break down to produce CS, so observations of CS in Enki's coma could help add understanding. We also imaged continuum emission, which is thermal emission from dust in the coma, and that allows for comparisons of spatial distributions between gas and dust. Next slide. All right. We aimed to characterize emissions from Enki's near perihelion, very close to the sun. We wanted to know, what is the movement and expansion speed of the gas? What are the properties of the gas? Is the outgassing uniform or asymmetric? And what is the spatial distribution of the dust, and how does it compare to molecular emission? To answer these questions, we created maps of HCN, CS, and continuum emission. These maps can be seen to their right. We extracted spectral line profiles from HCN and CS data, helping to understand the motion of the gas and whether it was red shifted or blue shifted, and the asymmetry of the coma. The spectral line profiles can be seen in the upper right corners of the HCN and CS maps. And we used modeling to understand the motion of the gas, the chemical composition of the coma, and the production mechanisms of the molecules. Next slide. To complete this project, we used CASA software for analyzing data from radio telescopes, and Sublimed, a program that creates 3D models of the coma. Next slide. We got results. We detected HCN, CS, and continuum emission. We detected an asymmetrical, generally red-shifted coma with a greater peak on the red side, as demonstrated by the spectral line profile. And we used Sublime to address the research questions and to understand the nature of Comet Encke's coma, which I will go into on the next slide. Oh, sorry. No, go back, I wasn't done. We were able to test whether each molecule was subliming directly from the nucleus or being produced by chemistry in the coma. We also started with modeling HCN because it appears as by far the strongest line, and then assumed some of the values we found to also be true for CS. Okay, now next slide. All right. The ratio of sunward fan to nightward side gas production was found to be about 3.8 to 1. As shown by the data for both molecules, the velocity or expansion speed of the sunward side was faster. The relative abundance of HCN in comparison to water in the coma was about 0.2%, and the abundance of CS in comparison to water was 0.09%. The parent scale length, or length from the nucleus at which a gas is produced, of HCN had a 3 sigma upper limit of less than 75.8 kilometers. And the parent scale length for CS has a 3 sigma upper limit of less than 58.2 kilometers. Next slide. All right, here's what these results mean. HCN and CS are both present in Encke's coma. HCN emits especially strongly. The sunward-facing fan of the coma is about 4 times as productive as the nightward side. The 3 sigma upper limit of parent scale length less than 25 kilometers for HCN is consistent with a parent molecule production at or very near the nucleus. The 3 sigma upper limit of less than 60 kilometers for CS is consistent with a product molecule produced by CS2 photolysis, which is CS2 gas sublimating and being broken down very quickly into CS and S by photons from the sun. We did not find evidence for dust breaking down to form CS far into the coma, which has been suspected to be happening in other comets. The CHN to water abundance of 0.2% is consistent with other observations of Encke and with average values in comets. And the CS to water abundance of 0.09% is consistent with average values in comets. Next slide. Future directions. This project was only one part of the greater goal to study the nature of Comet Encke using ALMA data. I'm interested in continuing work on this project after college admission season is over and no longer takes priority. Measuring the full set of data, calculating upper limits for undetected species, and writing up a publication are future directions for this project. If I were to do it again, I would start the project earlier in the summer. We changed focus between multiple projects early on and before deciding to complete this one, which resulted in some delay, but not much. The biggest set of roadblocks, though, were challenges in getting the needed software installed and working on my computer. Next slide. Massive thank you to Nathan Roth for his expertise, patience, and excellent teaching while mentoring me this summer. And thank you to the N3 internship program for giving me this opportunity. And I'd now like to open the floor for questions.
Okay, well, first we have to congratulate you on a great project and a lovely presentation.
Yes,
And boy,
incredibly.
did you learn a lot about comets? Did you know a lot about comets before you started?
No, I did not really know much at all about comets.
But you sure do now. So that was a very, very interesting presentation.
All right, thank you.
All right, any questions for Anastasia? It's a very thoroughly presented project, I have to say.
But what was the most interesting thing that you learned?
How comets relate to the study of the early solar system. I don't know. I had no idea that they were as interesting as they are. And yeah.
Good answer.
Oh, great.
All right, well, awesome job.